Ma'am, shall we start, ma'am?
Yes, yes. Yes.
Okay, ma'am. A very good morning to one and all present here. It gives me immense pleasure to welcome you all for this 5-day faculty development program on Prism of Research Opportunities in Smart Grid and Electric Vehicle Technology, sponsored by AICTE ATAL Academy. Now I request our coordinator of the event, Dr. L. Premalata ma'am, Professor, School of Electrical Engineering, VIT Chennai, to welcome the guest of this session, Mr. Jayakumar Kannan sir, Director, We Lead Consulting, Canada. Over to you, ma'am.
Okay, thanks,
Okay, thanks,
Tasila.
Basila.
Good morning to all. On behalf of School of Electrical Engineering, VIT Chennai, we the coordinators of this FDP warmly welcome our speaker of this session, Dr. Jayakumar Kannan. Jayakumar Kannan has received BE in Instrumentation and MSc in Chemistry from BITS Pilani in 1996. He started his career as a system engineer in Wipro in 1998. Later in 2005, he worked as senior project manager at Simcor, Ontario, Canada. He has almost more than 12 years of experience in program project management, delivered solutions to banking, payment, retail, e-commerce, healthcare, insurance domains. Most recently, he leads digital transformation of SingPost. He is an expert in payments, project management, and digital projects. At present, he is doing his dual role as a director in WeLead Consulting Canada, and also he is working in RBC as senior project manager at Ontario, Canada. He has delivered web, IR, and image processing, check processing, payment clearing, logbox services, e-disbursement services for check stop payment to leading FIs in North America. He has recruited, coached, and developed project managers and created high-performing team. He has assisted with Data Analytics 2020 roadmap also. He delivered integration to Singapore Net's mobile-enabled payments for more than 150 services, migrated from mainframe to J2EE, mobile-enabled logistics, track and trace, modernized post office and kiosk, delivered end-to-end e-commerce, revamped SyncPost.com using modern tools, managed indirect team of 200, managed multiple vendors including Capgemini. Sir is one of a specialist in artificial intelligence, and today he is going to deliver us a technical talk on anomaly detection in electrical vehicles. We welcome you, sir. Over to you. Thank you.
Thank you. Thank you for the wonderful introduction. I just want to say good morning to everyone. Right now, I'm located in Canada, so it's almost night for me. But I'm ready to give the speech and share what I have related to anomaly detection, artificial intelligence, and the industry and various other backgrounds. Any point in time, stop me and ask questions if you need to. I will ask questions, so you can also ask me questions. So do not hesitate. If something is not clear, definitely stop me. The whole purpose is to share what I know in this field. So having said that, let me open my presentation. We'll go into it slide by slide. I'm not starting with the glossary, so I'm starting with this page here. Are you able to see my screen? No, right? I haven't shared. 1 second.
Yes, not yet shared.
Not yet shared. Yeah, just a second. I'm going to say present the entire screen. Okay, share. Okay. Okay, I believe now all of you can see it, right?
Yes, sir. Yes, sir.
Okay, if there's any delay in my speech, just let me know because I am actually seeing what I'm presenting. I'm not seeing you guys. So if you need me to stop, let me know, okay? So cars, AI, and anomaly detection, that's the topic on which we are going to talk. Basically, I'll walk you through the industry, how it is, lead you to a specific area and talk about that, lead you into artificial intelligence. It's not a buzzword anymore. A lot of companies are using it and experimenting with it and putting it into real world systems too. You may know some of the cars have already been tried. in the real world and all that without a driver. So it is a fast emerging field. We'll go through some of the interesting things that has brought this in place today, and then we'll get into some technical details. It will be bit technical, so if it is too heavy, let me know. I've tried to simplify a lot of things, so let me know if it is very difficult. I'll slow down or reduce it or whatnot. Okay. So having said that, let's start with one of the most interesting facts is basically that if you go back in time and see what were the cars that were originally made in the beginning, you will notice battery operated cars were there at that time too. It is not something that we 100 years later are thinking about it. It was there in the beginning. At that time, people didn't need to go far away, like how people travel. Here, I lived in Chennai for a while. I'm from Tamil Nadu, so I lived in Chennai for a long time. I used to drive till Kanyakumari, 11, 12 hours at a stretch, right? So that was not there in 1800s and all that. They just needed a car for just locally driving and to show their status in the society, and things like that. And science was growing a lot at that time. So battery operated cars were actually made at that time itself. Why it did not fly high, why it did not pick up, is because in parallel a lot of other things were happening. I've just jotted down a few points here. Economics of having that car. Sometimes you will just blast on the driver and the whole thing will become dark in color. So that reliability sort of issues, and then politics played a bit of factor, and fossil factor played a big factor here. Basically, gasoline took over, petrol took over, right? Cars were made to run much cheaper on that. It was very cheaper to get that compared to battery operated cars. But we are now here talking about electronic vehicles, IoT, and artificial intelligence, and cars that can run for a long time. Trucks run for a long time on lithium batteries today. So it is a very interesting world that we live in. Just to give a context, because a lot of text will just be boring, I just picked up a picture of how one of the olden cars looked. I know all of you know it. I just wanted to put some interest there. By the way, any picture, any reference that I'm doing, I have in my last slide, I'm indicating where I picked it from. I've leveraged some research that has already happened, sometimes Wikipedia, sometimes other journals and articles. So everything is linked in the last page. I'll share it with the Dr. Premalata after this session is done. Okay, so that is what happened in the early stages. Where are we now? So now, to a large extent, India as such is biggest emerging economies, right? Why it is a big emerging economy? It's the middle class population is rising very high. They are saying every second 5 families are entering into middle class, the world over, I mean. So that means a lot of demand for a lot of goods. Better life typically means a house, a car, a good education, good schools, things like that, good vacations and all that, right? So the world is moving towards that. As such, the demand from the people is getting higher. For example, when I came here, the first car I had to open the window with the lever. But now there's a lot of technology which does it for me. It also understands where my seat should be positioned compared to where my wife would like to position her seat. It understands all those things and does it by itself. So it's very interesting how much of electronics and logic and thinking have gone into please the customers and the consumers. So it has developed a lot. All of you know that. So car owners today expect a lot compared to even 2-3 decades ago. They expect a lot, particularly in Canada. In December to May, it is cold, so the steering wheel is heated up. So it is very nice to hold it in the winter to drive it. So a lot of interesting features like that have come from some of the very bright engineers who are out there. More seriously, the security features are very high in nowadays cars. Will it take the impact in case there is an accident? Will somebody be able to get into the car? If somebody actually steals it, how quickly can we locate it? Even cell phones have that, right? So all that technology is coming up. Besides, one of the major driving factors is competition. Um, competition is driving a lot of this. Companies want to be very competitive to the consumer demands. Um, I just want to share a small story about this. All of us may know, if you take any Tamil movie or any Indian movie taken 20 years back, when a politician or some important person comes, 40 ambassador cars will follow. But today we don't see that. A variety of cars are there nowadays, right? India opened up the market somewhere around 95 something, and that's why all this difference is there. If you take any movie made before that, everything is an ambassador car. The curious thing about the ambassador car is nothing changed in the car since India got independence, because there was no competition to change it. But you can see the landscape now, like every car, every year, new features are added, and that's how the market is. So what I effectively wanted to say is the landscape is very dynamic. A lot of things are happening. We have been talking about end consumer, but inside the technology, the engineering, the amount of work that's going on behind is it's even more exciting. So I'll share a little bit of that today. So given that the landscape is so big, we need to reduce the topic or look into what we want to talk about. And the topic is anomaly detection, so we'll get into that. So I'll get into the other slide. By the way, is my speed good enough, or do you want me to slow down? Or so I'm going to think that it is good enough. So I'll continue. Okay, so what are we talking about? It's good. Okay, so we are going to talk about how to detect when an anomaly occurs, how to reduce it, how to, or at least eliminate it or reduce it. Primarily, anomalies is also a sort of a broad topic, so I'll drive us more towards attacks into the car, because that's a sort of an interesting area which is emerging rapidly too. An anomaly as such, in English we just say something is abnormal, that's an anomaly. But if you bring a data scientist or a data expert or somebody who keeps on looking at data, or a statistician, they would say an anomaly is an outlier. Outlier is something like, suppose you have a lot of data points you've collected and put like this in a graph. The green line that you see is where most of the points are centering around. The red ones, particularly the ones that are far, far away, you can call them as outliers. All of us know that. I just wanted to illustrate that. So that's what we are talking about. I'm using the terminology DNN here. In the last slide, I've given a glossary of all these small terms that I'm using. So do not worry about it. It's further there. DNN basically stands for deep neural network. That's all what it means. SVM actually means support vector machine. That's one of the ways DNN learns its data. So we'll cover that a little bit later. But clustering is something that can be used to classify an anomaly. When you have a set of data, when you try to segregate them, you will find some of them fall into a specific pattern, some of them do not. So you have already clustered them out. Which cluster is an outlier, which cluster is an anomaly, we'll discuss that, but that's sort of what I mean to say. Anomaly means a variety of things to different people that come together to put this all together. Okay, so with that, let me get into the next slide. Okay, I have a question. I need somebody to answer. What is the anomaly in the statement there? Vanakkam is how Tamil people greet each other. Anybody want to answer that? Anyone? Someone? Let me show you the question again. So that is the question. In this statement, can any of you see any anomalies?
Sir, Vanakkam is the only non-English word. So that
Okay,
is
so
where you have already given the answer.
yeah, you're
That is why
choosing
I
B.
don't want to say hi and hello. I am using something more traditional so that,
Okay,
people get the good feeling of common
okay,
community.
okay. Okay, I'm just going to call you by the name, so my apologies. Thank you, Subhashri, for answering that. Okay, so I know this is the logical choice a lot of people would use. Any other answers? Anybody want to dispute that? Okay, I'll move on. So basically, if you look at it, right, if you have trained your system to understand Tamil language, I'm just leading us towards choice number 4. If you have trained your engine to understand another language, it's not an anomaly. It will understand it. If you have not done that, then of course it doesn't know the meaning of the word. So it'll probably say there's an anomaly there. It's just a fun question, so don't worry. I'll go on to the next slide. Okay. Ah, so why anomaly detection is important? I just want to cite an article that I recently came across. Sorry, somebody wants to say something. Okay, so this was actually done, physically done and proven that remotely, because the cars nowadays have Bluetooth and a variety of ways you can get into it. You could actually manipulate the odometer, which means drive the car for 1 lakh kilometers and change it to 55 kilometers and sell it. You can turn the engine off, which is very dangerous. You can just make sure the door doesn't open, or you can disable braking. You can take control of the steering wheel. So when the car has to turn left, it turns right. All sorts of wrong things can be done if people get access into it. You would imagine the car is very secure. Let's have a look at that. So that is the landscape on which we are going to continue this session. I'm going to give an idea of what is there inside this car that is making it vulnerable and what could be done about it, how AI helps with it. We'll look into that. What are the actual issues, vulnerabilities? You see, when you build, in olden days when kings built the fort, they knew that if they put water around it, it's very difficult to breach, right? You might have seen a lot of the Rings movie or many other movies. So it is filled with water and crocodiles are let there, right? So they know if it's connected by land, it's a vulnerability. So in the car messaging architecture, what is it that's leading to these vulnerabilities? We'll look at it. And then what is the remedy? How have we fixed it and how AI is helping? I'll also lead you through some of the AI is a very broad field. So I'll lead you into some of the things which are there. Particularly, I'm citing two research papers, 2018 and 19. I'll take you through the details of that. And I'll also share basically what happens in an AI. How does it actually learn? What is it doing to learn? And how does it improve itself, so on and so forth. With some examples, we'll go through that. Okay, let's get into the next slide. So CAN is basically controller area network. Even if you take some 40 years back, not more than 10 or 20, I'm just guessing, I don't know the exact number, things would have been connected in the car with electronics. But today it's more than 70 is what I'm hearing. So what we are talking about is what is the speed of the car, in which direction is the car turning, do the tires have proper air pressure, and then is there any remote transmission required, and then how do you say it, is the car skidding? There are various parameters like that which are continuously monitored in the car. The whenever we talk about this, right, there is something that's sensing the information, and then it has to tell the information to someone or some other unit in the car. So it needs a bus to send the information. So this bus is basically the CAN, controller area network. All these lines that you see is basically the bus through which various devices talk with each other. and naturally it becomes the backbone. You can even compare it to a human nervous system. All organs in the body communicate with each other through the backbone. I mean, they don't communicate with each other, they communicate with the brain, but I'm just using it as an example. This was originally designed for basically communicating. That's it. The tire wants to say something. It wants to say, I have a air pressure problem. It says it. It was built for just communicating in an efficient and fast way. The makers also thought tomorrow we may add 4 or 5 more sensors to the car, so they made it scalable. That is, they didn't make it difficult to add new devices. So that's one of the key features of this architecture. Plus, it also has a prioritization. Like, for example, if one of the tires is blown, it has no air, it has to say the car has to stop. Or if the car is skidding, the braking system has to properly engage to stop it, right? So that is a high priority message, right? Something that's related to temperature in the car is low priority. So this architecture, this bus understands which message is high, which message is low. Whichever message is high, the different systems understand that and they operate on that. For example, when the car is skidding, typically you don't give continuous brake because it will skid more. So the brake is on and off and on and off. So that sort of engagement is orchestrated through this bus architecture. It's not that the lines here is going and breaking it, but it sends the message. So that happens. Basically, it facilitates communication, and as I mentioned, more than 70 ECUs are there. ECU means electronic communication unit. Each one of these boxes could be different things that the car is sensing. Those are all ECUs. So they get transferred through the bus as it is. Okay, any questions here? If you have any questions, I can help out to answer. Okay, I'll move on, but if you have a question, I'll stop, okay? Okay, so if you draw a logical diagram, this is how it is going to look. All the sensors are going to be represented this way. It's just a diagrammatic representation. It sends an information. No, and sorry, question paper went down. So here, this is the structure of the message. We don't need to really sit down and understand this, but if you are intending to implement any of this, you may need details of what is inside this message, or if you've already done, you probably know this. Either way, I've given a link from where you can get all this information if you need it. So basically, the frame is starting here. It has an ID. This is what that gives the priority. That's why it's called arbitration. It gives a priority for this whole message. If the number is low, the priority is high. So that means a 0 has a high priority. So something to keep in mind. And then there are a whole bunch of things. And then this is the actual message, which is here. And this tells how to check whether the message is good or not. All messaging systems have it. I'm very sure you all know this. And then there's an acknowledgement that the data is good, and then few other bits of information. There's usually, I believe nowadays it's about 512 bits or something like that. But that's how this generally looks. If you get into why this is, why would this cause a problem? This is such a simple system. It allows multiple things to be added on it, right? I'll tell you what has happened. Number one, this is a bit old technology, which is, when I say old, 1985. 1985, Bosch created this, and a lot of other car companies started following it. Now that you have everyone using it, you cannot change it unless fundamentally the bus changes, right? So it is very difficult to go back now. So if some mistake had happened, it would remain in the system. De facto standard means everyone is using it. The only problem is when they originally built it, they did not have security in mind. They did not have all these remote connections into the car. You cannot Bluetooth into it. All that stuff was not there at that time, so they didn't have security in mind. But now everything is open, right? You could get in, you could hack into the car as such. And we all know now the car industry is moving towards driverless car. So what happens if somebody hacks into it? It's very difficult to even think about it. So that is how the landscape is. And then this is another interesting thing, probably a technical interesting thing, is it's a broadcast architecture. What it means is if this unit is sending something, it does not know who's receiving it, or it does not even know who's going to use it. It just broadcasts in the bus. So anybody, any other ECU can pick it up. That's why when the car is skidding, the brake unit, when it receives the 0 message, will start applying itself to stop the skidding. Things like that. I'm just giving it for an example so you can imagine. So that's what this is all about. So you can see, and nobody checks anything. Everybody can dump information into this bus. Whoever wants to use it can use it. This all sounds like a sort of a recipe for a disaster, right? So that is sort of where the vulnerabilities and things come up. On one end, if the architecture is like that, it is scalable. You can add any ECU into it, it will start working. But then it exposes these difficulties. So that's where we are. Okay, I just want to ask if any of you have any questions. Okay, I'll go to the next slide. I have a question. Can anyone answer this? How many ECUs does a modern car have today?
70.
Okay, very good. And that is Dr. Jamuna, right? Very good. Thank you. Okay, so let's continue. Okay, this is where I mentioned about the bit of a technical side. What I have tried here is converted what the researches that have happened and documented to something that's easy to share in a session like this. This is my own creation on the right side, examples. Even the terminology that I'm using is not real CAN terminology. CAN terminology is all hexadecimal. So if I put 20 of them, even I will not be able to follow it. So I've converted them to English. So tomorrow, if you look at the slide also, it'll be, oh, okay, this is what Jayakumar was trying to tell us. You will understand it. So I simplified this. Okay, let's see what the villains out there can do. That's what I call as adversary capabilities. Depending on what they know, they can be classified as weak, medium, or strong. Let's take an adversary or a hacker who is capable of sending random packets into the bus. Somehow they got hold of the bus and they're sending random packets into it. They are a weak adversary because the maximum they could do is send something like junk message. Okay, but if they become medium capability, well, it's just a terminology. Okay, I don't think this is out there in the real world, but if they are able to mimic a particular sensor which is in the car, let's say they are able to mimic the climate control. If they say the climate is not right, if the message says the climate is not right, the fan may go faster, or the heater may go faster, or the AC may go slower. It can cause these things. So they are a slightly stronger person because they can actually send the message on behalf of one of the sensors in the car. They have hacked into it. If they get the capacity to go and compromise other sensors in the car, then they are called as a strong adversary. That's when they start taking control of all the devices in the car. That's a dangerous situation for us. So let's see what they can do. Some of the attacks that they can do, the random ID attack, which we talked about. Before we get here, I'm going to use this a lot in the next few slides to indicate what's going on. So TPMS is tire pressure monitoring system. CLIM, I just put it myself, climate, and SPED is speed, and SKID is skid. I'm just making this up. So there are 4 tires, so you get 4 messages. Number 9 means low priority. That means the tire pressure is okay. And then the speed is decent enough. It's number 8, no problem. The car is driving properly. Skid is also low priority. There is no skid going on. It's just monitoring and sending this. Let's assume that every time slot we can take a second or microsecond, doesn't matter. Some time slot we get these 10 messages. That's a normal car is driving normal on the road. A random ID would something look like this. You will have all of a sudden one of the tire pressure monitoring is gone and a random message is dumped into it instead. So that's how that would look. And I'm using red color to indicate hacking, so it's easy for you to see on the slide. All zero ID attack is another attack. What they do is they send this junk message with high priority a lot. As you can see, 1, 2, 3, 4, 5, 6, 7, 8. It keeps on coming. What it does is all the ECUs think something is going on in the car, and when they get overwhelmed, we are talking about thousands and thousands of this coming out. The system gets overwhelmed. The bus itself gets overwhelmed, and it may stop looking for any message as such. So that is called a DOS, denial of service. The ECUs no longer can send nor listen to the messages. Fundamentally, they've broken the bus. Replay attack is a sort of a medium sort of attack, because these hackers or these people know how a regular message looks like. They take the regular message and dump it in the bus. So for example, you can see the 4 tire pressure, 1 climate, 1 speed, and 3 or 4 skids. That's a valid message, but that gets dumped inside the bus all of a sudden. So that sort of attack is called as a replay attack. Spoofing is you are actually mimicking someone, and this is you're mimicking one of the ECUs, right? Mainly because there is no authentication and all that. All of this is very easily possible. Let's assume the car is skidding, but look at the message. The skid message is number 9. It is low priority. It is supposed to be high priority because the car is skidding, but somebody has taken over that particular ECUs, so they could do such things into the bus. A drop attack is one ECU is completely compromised. It's not even participating in anything. So I've just put here as no data, but it will actually look like this 5 and then this 3. There won't be anything here. So that's how that looks. This is just an example to set stage on what these people could do once they get into the car. If you are doing projects, or if you've already gone into the system, you may have seen a multitude of these messages, and you could relate them to how different attackers can manipulate those messages. Okay, I'm going to go to the next slide. If you have any questions, stop me. We can always come back here. So logically, before AI came in, somebody would say, you know what, these are all simple things. We can easily solve the problem. For example, a variety of strategies are there. If somebody is sending a message with an invalid ID, right, you can very easily figure it out. Let's take the first letter as the ID, T, 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 A, C, S, 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 SK, whatever, right? So if these are the valid IDs, it's very easy to say which ID is wrong, because all these messages are pre-programmed into the car. When the car is manufactured, it is actually burnt into the car. As a result, we know at that point which one is valid, which one is not valid, and it's very easy to figure out. So suppose this message comes in, with a simple software, you can say ABCD is wrong, just ignore it. So all the ECUs will ignore it. In other words, the ECUs themselves are programmed to not look at IDs that are invalid. So you could do it that way. Time interval. So I'm extrapolating a lot here just so that it's easy to follow what I'm trying to say. In real world, this could be much complicated than this, but just to help you imagine, I'm sharing it with an example. We know that there are 4 TPMS messages, 1 climate message, one speed message and 4 skid messages, right? Logical. There are 4 tires. Any of the tires can skid, but the climate in the car is one temperature. Speed is 1 speed for the car. So we know that these 4 messages are together. They always come together, and the skidding messages come together. If that is broken, then of course we know somebody has got into the system. So it's easy to detect. A simple software will once again will easily detect it. Frequency distribution. If you take a flooding attack that has happened, like somebody has dumped all these random IDs into the bus, we can very easily see that the frequency of that message is very high. And by the way, some of the researchers indicate that if you really want to break the system, you have to flood it. Just randomly sending 1 or 2 here and there would not work. You have to literally flood it. So this is a very easy way for a software to say, I'm seeing a lot of these junk messages, so I'm just going to ignore it. The software you can do it with that. And then message sequence. It is very similar to time interval, but it is more at a message level. Because we are dealing with a simple scenario, I couldn't point it out to you, but in a normal car operation, sometimes the pressure will go on one of the wheels, or the speed may be not good for the car. It may skid or introduce skid. So all of those are shared as messages. Those are real anomalies, by the way. But that doesn't mean the car has to stop running. So we need a way to differentiate that a real problem happening in the car versus somebody spoofing it or attacking it. So how do we do that? So that sort of thinking is what we have to get into. So that's where the message sequence plays a lot of role. If you take the operation of a car, so the data projects, the neural network development literally requires a lot of data. We have to collect a lot of data for it. So when you look at all these messages, we ourselves can identify patterns. So that's what we are trying to say here. The sequence of messages when something really goes wrong is something we can predict. And the software can be used to detect those. And if somebody is doing something different than that, then we know that it's hacked or something like that. So that's what that means. So let's quickly go to the previous slide. So we have a variety of attacks which are there, and a variety of ways in which, without using artificial intelligence, we can solve those problems. And as I've indicated here, these are simple computer logic. So I want to pause and see whether we can answer this question. Can anyone identify what sort of attack is this? So I'll give a clue. If you see the red text, that is the attack. You can see that's a regular message, like a proper message. 4 TPMS, 1 climate, 1 speed. And I'm sorry, I should have put 4 skids here. I put only 3. So it's a proper message, and that's being dumped into the bus.
Is it replay?
Yes, it is replay. That's once again Shubhashree. Okay, if there was no COVID, I would have come there and given you a chocolate. Okay, so let's go forward. So yeah, that is basically a replay attack where the hacker understands there's a logical message. Just for the fun of it, they just put it into the bus, and it causes problems. Basically, you're slowing it down. The devices may not tune into it, denial of service, various other things can happen with this. It's an anomaly. Okay, so far we have seen how software can help with a lot of these problems. Just a second. Okay, what the paper did is, what the article was suggesting is, basically a lot of these problems, as we noted before, can be easily identified by a simple software. And when I use the word simple, it doesn't take that much of clock time to run it. So the car can efficiently identify those and remove them from the stream. But instead of doing that, if we take everything and send it into the deep neural network, as you already, most of you may know or have done this yourself, deep neural network is a lot of computation, and it is not the right use to use simple things into the neural network to see what it is going to say. So a lot of those things have been when the rule system identifies it, it directly goes to response. When it is not able to, what it means is none of the rules are fitting. For example, all the IDs are valid. The message as such is correct. There's no problem with it. It is a legitimate ID, legitimate priority, but it's still a hacking system. It's a bit sophisticated than what we have seen. We will cover that bit later. Then you would need a DNN-based system to identify that. So fundamentally, instead of passing everything to the neural network, a lot of things which we identify, it's very logical. You just get rid of it and use this only when you need to. So all the things that we just discussed in the previous slide, the valid ID, the time interval, how these messages are distributed, what are the sequences, all those things are collectively called rule-based system. Okay, now we get into why artificial intelligence actually is needed. So sophisticated attacks. Once again, I'm trying to help imagine with an example. It may not be a real world example, but it allows us to imagine. So when a sophisticated attack happens, the rules just bypass them. For example, if you take a message like there are 4 tire monitoring, 1 climate, speed, and then you can see there are 2 skid messages coming at 5. And then, of course, the brake needs to be applied. So a 0 brake, 0 means high priority, message is given. 2-wheel skidding and a brake is requested. We can see the ID is valid, the sequence is valid. When I'll explain this word a little bit later. What I mean to say here is how organized the data, the messages actually are. Somebody requesting to brake after 2 tires are skidding is logical. So there is no, there's nothing wrong in that. But should the car brake? That is the key question. So I want to lead us into, this is a simple thing. This is a single 1-line, 1 time slot message. But when a number of these messages come, how would the machine actually decide whether this is an anomaly or not? It is very difficult to decide that because everything appears legitimate. If somebody had spoofed the skid, meaning they are mimicking there is a skid. Okay, somebody has spoofed it, they have hacked it, and they are sending these 2 5 skid messages and a brake message that the car has to brake. But in reality, the car is not skidding. It has been a message that has been injected by a hacker or someone else. So how would artificial intelligence decide what to do with this? So that is the crux of the problem. On one hand, if we brake and there was no problem, it's not right. Somebody behind is going to be in trouble, right? Because these things will just break means it'll break. Whereas if there was a real problem and we did not brake, that's also a problem. So we are walking on a thin line. The entire industry behind artificial intelligence or these networks or learning networks, machine learning and all that is walking on that thin line. Should I accept it or not accept it? So how we do that? And by the way, end of the day, when we put all this in the car is going to make the decision. So it needs to be a good one. And I'm very sure a lot of us are aware with the experiments that Tesla had done, Uber had done some experiments, and there have been some fatalities too. So we have to keep that in mind while developing all this. So that is where it is very easy to just say AI will look at the pattern, it will understand the pattern and all that stuff. but we'll actually look at what it is actually doing. It is patterns, but how it is doing it is very interesting. We'll look at it. So that is the core of the issue, and we'll get into the details. So what it fundamentally can do is learn from patterns, from the data. For example, the simple computer logic which we talked about, those are patterns that we ourselves recognize. When you expand that to a software which is thousand times more capable, it can do a lot more. It just extrapolates to even hiding small patterns. Based on the pattern, it will make a decision. Whether we accept the decision or not, that's a different story. For example, I work in banking today, right? So one of the things that the banks are trying to do here is we have a lot of youngsters now. The population of youngsters is also getting very high. They don't monitor the bank account like our parents used to do or we used to do, depending on your age group. Some of our parents would literally write everything down and monitor what's going on. Today, the young population that's earning doesn't even look into the bank account. So my bank, the bank that I work for today, has come up with a artificial intelligence based analysis. It looks at 12 to 24 months of all your transactions. It understands how you spend, how you make money, what are your interests, what do you subscribe. It knows a lot. And if it feels that you may be missing a payment or you have lost a job, it will give an insight saying that the next bill you may not be able to pay. You may want to move money from some other account into this account, otherwise you will end up paying a fine to the bank. So this sort of analysis and insights are coming up. Although that decision is done at the AI level, whether we want to use it or not, we have another small layer of software. So that's why I'm saying, although the car can make a decision, we can still present it to the actual driver and they can choose to use it or not. The AI system can also take feedback. I am sure all of you are aware of that. We can, of course, alter the decision-making process. That's the example that I gave. So fundamentally, it's very good at processing a lot of data and self-tuning towards the right decision. So when we say this statement, right, it can process a lot of data and give us a good decision. A nice way to measure, or if you start digging a lot deeper, or if you start building these sort of systems in your research labs, one way to measure how good we are is how many wrong decisions are coming. It could be an anomaly and the system did not detect it. It is not an anomaly and the system says it's an anomaly. So the percentage of that, however low it goes, that's how good the tuning actually is. So we can measure it with that. So basically what we want to carry forward is the ability to learn patterns is the key, and the ability to process a lot of data, and how close are we to reducing the percentage of these false positives drives the quality of the network. Okay. So this block diagram, it's very logical, right? So if you end up studying a lot of materials related to this, a lot of technical terms come up. But honestly, under the hoods, there is a very simple logic of what is going on. We, as such, can easily understand it. What is going on is we are giving it a lot of training data. And some of the research papers that I have referenced use around 2 lakhs to 30 lakhs, something like that, of machine messages that have been sent out. So that data is presented to the deep neural network model. How it works, we'll deal with it later. I'm actually going into the details a bit later. So the network looks at the data and it says, this is an anomaly, that's an anomaly, this is not an anomaly. It just categorizes the whole thing. And then we, from our end, also know which one is an anomaly and which one is not. So we give that feedback. We say that this is a good decision, this is a wrong decision. So it receives the feedback. and it understands what's the gap. So the network came up with something, and we are coming and saying this is the right answer. So it understands the difference. And there are a few other diagrams. For now, imagine that the network understands the difference between what it has predicted to what is the correct answer. So that goes back into the network again. And the way it calculated this whole decision, it changes some of its parameters. And once again, it starts predicting. And then it ends up with new results. We go and say, this is right, this is wrong, this is right, this is wrong. Once again, it understands, there is still some difference in how I'm predicting. It takes it back, changes the parameters, and gives the decision again. So this loop is repeated a lot. And at certain point, we as the creators of the model are satisfied with its output. The percentage of error becomes very low. So we say that the model is ready to be experimented in real world or taken for further testing and so on. So typically we have training data and some amount of test data to actually test it, to reach a point where we get a model. This term is also sort of interesting because that is what actually patterns, it actually refers to patterns. So when it looks at the data, it understands some patterns in it, and it tries to segregate the full data set, saying this part is accepting the pattern, this part is not accepting the pattern. So it makes decisions based on that. For now, we can imagine it as detecting patterns in the given data set. So now you can see how important is this data set itself. If this is wrong, then the model is going to be wrong. So it is very important that we have a lot of data to support it. And I'm very sure all of you know, when you browse YouTube or when you have suggestions and recommendations on any mobile app that you're using, all of them are using this sort of learning. If you accept what it's recommending, then it thinks that it has done a good job. I'm using the word thinks. It understands that the difference between what it predicted or recommended and what you've chosen is nothing. So it won't go and modify itself. But if you didn't choose it, it goes and modifies itself. Similar, same principle applied everywhere. Okay, I'm going to go out of this slide and let's see what's there next. Okay, I have a question. Who can answer this? Which one would you choose? Learning, computing, thinking, or decision making? Sorry? I'll show you the slides again. What is AI good at? Which one would you pick?
Decision making.
Okay, that's a very fair answer. It's a fair answer. Anyone else? Okay, let me continue then.
Primarily, AI techniques are learning basically.
Yes,
learning from the data, learning
All of
from
this,
the pattern.
all of them also. Yeah. Purposefully, I put this question in a confusing manner. I just want to know who answered. Who was that answered?
myself, Vinod Kumar.
Vinod. Okay, good, Vinod Kumar. And the other person too, I believe it is Subhashri or someone. Good answers. This is purposefully I made it this way because it's a lot of technical information. A pause like this is good for all of us. So definitely it's good at doing all of this, and one leads to other. If you look at computing, it's because of the ability to compute, it's able to learn. Because of learning, it's able to decide. I just put in the word thinking here. We'll talk a little bit about it later. Is the AI really thinking? A lot of us use the word, but I personally think it is not thinking. It is just executing a program. But we can leave it to our own perception. Okay, so let's get into the next one. Okay, now I just want to take us into what is it that the network is looking at, the neural network is looking at. Once again, I've used examples so you can easily imagine. If you are doing research or conducting research, you can do the parallel with the real data set. Okay, once again, I'm using my branded normal message. 4 TPMS, 1 climate, 1 speed, and 4 skid messages is a normal message for the sake of our argument. And what you will notice is, so until now we have done rules, right? We understood whether an ID is valid or not. We understood how things repeat. We understood the frequency distribution. Like if you take 1,000 messages, how many times TPS-MS comes when the car is running normally versus abnormally, all those data is there. But when we talk about DNN, for each one of those, we need to remember the network can go into the data and identify very, very special and specific patterns, which were not apparent to us. But the machine can, the software can do that. So we're going to talk only about message ID, and you can see how many different things it can do. So from a large set of messages, DNN can basically say what is the acceptable pattern in a normal message for how many times, okay, this one is appearing here. How many times these messages are appearing? I'm just using our example here. Here it is 4 times, and this is skid is 4 times, and climate is 1 time. But if you do a similar analysis, or if you let the neural network to do a similar analysis, it will produce a graph like this, or it will have in its a memory, so to say, a pattern like that, and it will use that pattern to say any incoming message is valid, is an anomaly or not. It will be able to do that. In the next slide, what I have here is this is actually the real IDs which are found in the CAN network. I couldn't actually get the actual names for all of these. I tried a little bit. I could find only few of those. But anyways, these are real messages, and you can see how the distribution is over a set of 21 lakh messages or something like that. This is how it gets distributed. So this forms a pattern which the network learns. Anything different from it could be a real anomaly, could be a malicious attack on the system. That decision we'll get to it later, but the system actually has a baseline. A normal distribution looks like that. So that's what the the deep neural network will do. Okay, now let's get into a different dimension of the same information. The relative distance between the different messages that are coming. I just, for the sake of our discussion, I just picked up 2 messages, and you can see I put this as phi. That means there is some pressure problem in the tire in one of the wheels, but the car can manage it. There are cars that can automatically inflate if the tire is losing the air and let it continue, but it would still send out a message like this, something like that. So you can see from one TPS to another TPS in a normal scenario, the distance is 1, the distance is 2, the distance is 9, 10, and 11. So we take the average distance for this particular message. Like that, we compute the average for various other things. In our example, I'm using only TPMS. So you will notice when there is an attack on the car, The car, in our situation, the car is actually running properly, but the TPMS is coming up with a 0 saying the tires pressure is gone. It cannot drive if one of the wheels is gone, right? But the message looks like that. So the distance between these TPMSs gets distorted a lot. How it gets distorted is, I'm just graphically representing it for you. In a normal message, you would see this sort of distance, and that's how a normal message looks. A lot of messages look like that. Some set of messages which are for the phi, when the phi occurs, it would look like that, the distribution. And where the hacking has happened, you can see it happens very infrequently. From our perspective, we are able to imagine this, we are able to understand this, that when a hack happens, the distribution gets distorted like that. The deep neural network understands this sort of patterns in the data. And once again, whenever we talk about the neural network, we always think about a large set of data. And for our explanations, we are putting it like this. So it can understand the fundamental way in which data gets distributed when it is normal versus when there is a real anomaly happening versus when there is something really wrong in the car. This aspect is called as relative distance, and it measures it and goes based on that. This once again is one more pattern that it can use to make decisions. Okay, now we get to entropy. As I mentioned, I'll explain this now. Entropy, as we all know, is just how disorganized the system is. So let's take these two messages, which are normal messages, and then there's a flooding attack. So all of a sudden you can see the distribution is totally disorganized now. And when we calculate how much it is disorganized, you can see this sort of a distribution. The TPMs go, in other words, if you're getting only these messages, right, this is a normal message. If you keep on getting a normal message, there is no disorder in it. There's nothing out of order in it. So it would be 0. But when something like this flooding happens, there is a small amount of distortion that happens for all of this. Sort of a disorder. We can mathematically measure it. So this is a sort of indication or a sort of a pattern which the deep neural network can once again catch. So if we keep on thinking in this direction, there are a variety and a variety and a variety of ways, things that the neural network can capture out of it. A lot of experts even say that once a neural network model is fully tuned, we actually do not even know what it is looking for to give the decision. We just know the decision is correct. Mathematically, within our risk tolerance, the decision is correct. That's all we can find out. But under the hoods, there are a variety of things that go on. And I also have a visual example which will clarify this a little bit better. But from a CAN architecture, cars anomaly detection point of view, the messages that we receive, we could analyze in this fashion to put together a deep neural network. Okay, I just want to lead to the end of that particular research paper, and you'll notice it was actually done with a normal laptop. This is just a laptop that typically offices and institutions use. Nothing crazy about the architecture. And this is what they had used to build the network that learns out of it. And you can see the ratio of the false positive has gone down from 0.09 to 0.02 to 0.18. The main reason being this is the third car which is here, which has so much of messages, 21 lakh messages. Whereas if you see the first one, there's only 2 lakh messages. But for that difference, this percentage is decent. I just want to share the results, okay? How the network that we talked about, the different patterns that it used, eventually ended up coming up with very low false positives. Some of the interesting things is, I know we started with car, we went into the CAN architecture, we went into how the ECUs talk with each other, so on and so forth. But when we get into deep neural network, to some extent the work actually becomes more of data related work, and a lot of the tools that are available in the world today are all software based. They manipulate and they allow us to dissect and visualize the data. This is one of the visualizations which is there. That's what the different tools do. And under the hoods, the layers inside the neural network, they are all mathematical in nature, and as a result, software is the way to go with it. So you will have to be ready to get into software to put your hands into this area. But the result that comes out of it is more on the car side, or whichever industrial equipment or anything that we use and want to apply this, it applies to that. But the study and the research assets gets to the data level, at least till we train the model. Once we have a good model, we can apply it and see how the car actually responds to it. This is just a visualization I just want to show you. Here we found the anomaly, the correct anomaly. Here we missed it. This was a false alarm. This is also correct, but it's not an anomaly, so it was sort of rejected. So the whole data set can be segregated like this and can give you the percentage of what it had achieved. All of this is something that we can use to further fine-tune the model. Okay, with that, let me step away into this. Further to that research paper, there was another one where they had gone in. This is from 2019. The ones that we discussed so far was 2018, and this one is 2019. OCVSM is fundamentally a one-class support vector machine. Support vector machine sounds like a odd terminology, but what it is doing is it clusters the data like this. It knows what part of data is coming together by itself and what part of data is coming together by itself. So this can be called as a decision boundary. So you may have data here and there, but the neural network slowly learns and segregates them properly. If you've ever gone into TensorFlow, there's a nice demo which is there, which shows this, how you can manipulate the data any way you want. You give it, it'll take some time, but it'll actually segregate it. So basically it identifies the subsets within the overall data. And what the algorithm will do is, based on how it is segregated and based on the decisions that we give when we are training it, it will understand what's an anomaly. It will apply a boundary and it will say, let's say blue is regular operations. Anything outside of this boundary will be categorized as an anomaly. Once again, where this boundary falls, how it determines the boundary, that's all inside the neural network. But once it's done, you have a solution, and that thing is called as one class support vector machine. I think I made a spelling mistake here. It's support vector machine. Okay. And now what we have here is, this is an interesting thing that they did. What is very interesting is we all know that we learn patterns from the data. The deep neural network learns some patterns, and then there's an actual result. So there's a comparison. What did it predict, and what is the correct answer? So it understands the differences, and it takes that feedback back into the system for fine-tuning the parameters, right? So that's what it does. What this one is doing is, what these researchers have done is, on top of the simplest way, this term MBA actually means a modified BAT algorithm. BAT means the vowel. So we know that what the bats do is they use sound to locate their prey. So just imagine what it is doing, right? It sends the radar, and the radar bounces and comes back. So it listens to that information. So it knows where it is, and it knows where the prey is. It knows its current speed, current direction. It adjusts it based on the feedback, and it keeps on doing it. and it is called as an explore and exploit approach. When it exploring means it sends the radar, and when the radar information comes back, it's exploiting that information to get to the prey. So in a similar fashion, deep neural networks do the same thing. In a similar fashion, these algorithms which they have developed, each algorithm is considered as a separate bat or a bat family. So this algorithm would come up with some prediction. Similarly, another one will come up with some prediction. Another one will come up with some other prediction. You may ask why every algorithm is doing something different. Why not? They are all software. Why not all of them give the same prediction? The answer for that is the starting point for an algorithm could be anything. The algorithm itself chooses a starting point, or you can also give it a starting point. So because the starting point is different, what it predicts is different. We'll get into the details a bit later. So each algorithm provides a different result, and the algorithm that provides the best result is kept as it is, and the rest of the algorithms, just like the bat, will change its internal parameters so that it can come up with a better result. That's what I've indicated with the plus. These are all the algorithms that are changed because of this feedback, and it keeps on doing this again and again. And obviously you will notice that all of these algorithms get better and better with more and more training. It is very similar to a deep neural network. Only thing is, the entire neural network itself is a bunch of separate algorithms, and then they are competing with themselves to come out with the best. I hope I'm making it clear. If not, please stop me, okay? Anytime you can stop me. So that's what I've written here also. So I will step out of this slide. Let's have a look at this question. Name one of the features extracted by DNN that we studied so far. Message ID or system entropy or MBA
explore exploit.
Sorry?
MBA explore exploit.
Yeah, of course, yeah. That's right. That's the one that we just studied. So you have to give me something from the past, few slides back. I think we studied all of them. Entropy, we talked about it. Sorry, go ahead. Okay, so we talked about almost all of that. I just want to give a break. We went through quite a bit. So I just want to give a break. So that's there. Eventually, this is the result. I've given details of which car they used, what sort of protocol. I'll share this slide if it is of benefit to you. You can use the information if you're doing your research. And here 30 lakh messages were used. This is the one class SPM. It came up with this sort of a false alarm rate. It is fairly high, but that's what they came up with. And with this BAT algorithm, you can see it has gone down so much. We didn't talk about this isolation forest. That's another method where it's a very strange method. It's a very strange method in a sense that whenever we talk about anomalies, right, we want what is normal, and then the difference is an anomaly, right? But in this isolation forest approach, they just say what is an anomaly. They don't care about what is normal. It is a different way to approach the same problem. I didn't mention this, but I want to be fair and want to tell you what this means. And this was once again done with this sort of hardware. Believe MATLAB is available, and so on. Okay. Now I'm going to get into what DNN is doing, and I believe I have another 20 minutes, right? I think so. 12:30. We started at 15. I think I have 15 minutes. Okay, I'll try to wrap this up very quickly. Okay, so very simplistically speaking, if you have 6 or 7 data points like this, you have a starting point. You think that this is the line of best fit, and you know that it is not. you move it this way. For us visually, we can see that you have to move it this way so it fits, and then finally you put it here. That is the best fit. Any more you move, it's going to be wrong. How do we decide that? We decide based on the distance between the line to the different points. It's as simple as that. And that's what the neural network is all about. Of course, because the data set can be complicated, how it figures this out gets complicated. Other than that, at least my personal opinion is it's just a trial and error method to detect what's going on. If you go in under the hood, there's a lot of calculus, engineering, all that stuff which is there. Okay, in a three-dimensional model, we want to get to the lowest point. As we know, we can start anywhere. If we start here, we want to find where is the lowest point. We'll find a little bit of delta, and we know that, yeah, this is lower than that, and it goes here and goes here, goes here, and keeps on doing that calculation again and again, and it gets here. Why do we have to go to the lowest point? The reason is, what this graph is showing is, as I told you, right, the neural network comes up with a prediction, and we say whether it's correct or wrong. So that difference is the error. It's actually in DNN terminology, it's called the cost factor. So this graph represents the cost factor. So that's why we want to go to the lowest cost, which means we have achieved the best fit. That's why it's also called as gradient descent. Descent meaning going down, all that. That's why it's called that way. Let's see how it learns. Okay, this is where the real meat of the thing is. You may be aware that there is a data set called as MNIST, and I'm going to use a visual example, not a car-based example, because car-based examples is data. It's not that easy to imagine, but the principle is the same. You could apply the same principle for them. So here, this MNIST data set is basically a bunch of handwritten numbers, thousands and thousands of them with the correct answer. So in the database, you will see 0 and then comma 0. This one and comma 1, this one and comma 4, this one and comma 8. Even a third grade kid can very quickly read all of this, but a neural network will need some time to learn. How it does it is, let's take one digit. Let's say this is 9. There are 28 by 28 pixels. And the neural network as such looks like this. 28 into 28 is 784. So there are 784 pixels, right? All these small dots which are there, those are pixels. So each pixel has a color. Most of this is dark, so it is a 0. Some of these are perfect white, so it is 1. Some of them are in between. So it will be 0.8, 0.5, 0.4, whatever it is. So those are all the numbers that get here. Okay, and each node, this is called a node, communicates or sends information to another node. So all of the 784 talk to this. All of the 784 talk to this, and so on. And then all of these talk to each one of the node here. And then all of these talk to each one of the node here. So effectively what it is doing is, you can see these are green. That means they were probably white in color. The rest of them were black. Some of them are lighter. That means it was in between black and white. The way these combine, only some of those get highlighted, which means these are getting the pattern inside this number. These do not. And then the ones that get the pattern drive a further other pattern. And then the ones that have got the pattern here drive the final output. As you can see, it comes back and say this is number 9. This is the final result. In the beginning, it would have said some nonsense, but at the end, it will eventually learn when we send the cost factor back. Okay, so that's what it does. So visually, I want to tell you what it is doing. So this is 9, right? For us, it is 9. But what the network does is it splits it up into small pieces, or it recognizes small patterns. It knows that there is an edge here, there is an edge here, there is an edge here, and there is a long edge here. So this layer recognizes it. Probably some of these circles have recognized, maybe this circle recognized this part, this circle recognized this part, this one recognize this part. It could be anything depending on how these are connected. And by the way, we don't connect them, they connect themselves. So that's why we really don't know how this exactly is working, but we know that the overall thing is working. We have control on it. It's not like it's intelligent or anything. It's just doing calculus. That's all what it is doing. So those recognize these 4 separate patterns. And then when those patterns are combined, it recognizes a further, an additional pattern. And that's what this is. It puts these 4 together as it is shown in the slide. And now it says, yeah, all these 4 form a pattern. And I'm going to say that this is what it is. It doesn't know this is 9. It just knows that one of this lights up. And we call it 9. So that's what really happens. You could use this sort of imagination for any type of data. This is just some numbers and how many lines and wires are there. Some 13,000 lines are there and all that. It's not that important, but these layers will fundamentally change. We get this from the pixels. The numbers that these circles are going to get, the parameters, are driven by these connections. Whichever ones have recognized a strong pattern, they get lighted up. And from there, combined patterns light up, and then the final result is given. Sometimes you will have more than, this one has 2 deep layers, you may have more, but that's depending on the situation. By the way, this is a very nice video, which is available out there. I've given the website in my last slide. You guys can use it if you want to get deeper into it. Okay, have a question. What is the single most important thing the DNN layers do? It's the same question like last time. Maybe that's why you guys are not answering. It's basically learning. That's what it does. Just a little bit more and we'll be done. Basically, under the hoods, each of these nodes combine to light up or identify a pattern using a sigmoid function. There are many other functions depending on the type of project you want to do. You can choose them. Here you can notice the answer is always between 0 and 1. So all of these are between 0 and 1. That's a sort of a mathematical function that does this. Bias is something like if you have a 199.93, you can call it as 1.99 into 10 to the power minus 3, right? 10 to the power 3. Yeah. So you can call it that way. That sort of a thing. It just adjusts the number so that you can actually work with it. And this is the actual matrix calculation that goes on. I want to cover this, but I think I'm running out of time, so I'll skip this. And then once it has finally done the job, as you can see in the first slide, it actually showed only 9, but the first time it will come up with so many different numbers being selected with their own weights. And then we say only this is right. So it takes the difference and it propagates it back into the system, which means all these numbers are modified. Logically speaking, the ones that are bright has been driving these numbers, right? So those numbers get modified more than the unlighted ones. So it understands, it plays with these things like trial and error, and over time it learns to give the right answer. So last but not least, any data, any deep neural network related problem, basically the neural network is good for predictive problems. If, for example, the insight that I talked about for the banks, it understands the 2 years of data and it tells you whether you're going to miss a payment and things like that, right? So for prediction, this is the right methodology, right tool. If something is non-predictive, deep neural network is not the right choice. So before choosing, you may want to think through whether you're going to use it for prediction. The immediate next step is collecting a lot of data. I should have put lots and lots of data. The more, as you can see, the more the data, the false positive ratio goes down. And it's very important. Suppose we're trying to cure cancer, we don't want to want the tool to say some good treatment as a invalid treatment. It may cure few people, right? Similarly, some bad treatment should not be called as a good treatment. So we need to be careful about that false positive depending on the industry. And then we collect test data separately to test the system. Through that exercise, we do the feature extraction. What this means, once again, I already mentioned this, is the neural network identifies patterns, and there are a variety of names for that. The SVM, OC, SVM, a variety of names are there. Whatever it tries to extract, we fixate on that. If it works for us, we go with that. And then we build operating model, and we can use it to start predicting. And we have sort of reached a good milestone here. That's why I put that mark there. That brings us to the end of the last slide. I've given a list of terminologies that I've used. When I send it, you can have a look at it. I've also given various references. This is the MLA format. These are all the papers that I have used to produce this. And then some interesting sites. When I had my own suspicion or doubts about few things, I tried it. This article is very good. I think most of you would have read it. Both Tesla and Uber had an accident, so let's mention that. This slide, I cannot show it there. What it is there are a variety of learning methods. But under the hoods, everything does the same thing. They all look at the data, they identify the patterns, they predict, and they correct themselves. And at a certain point, we determine the model is good enough. That's what happens. When you correct the output, it's called supervised. When it corrects itself, what that means is we would have told them, we would have told the neural network that this sort of data is not an anomaly. So it always corrects itself based on that. So those are all various terminologies which are there. You can look at it at leisure. With that, I just want to take the opportunity to thank every one of you that have patiently listened. Hope I have properly shared what I know and help to understand few things. I want to thank all of you, people who answered. Special thanks, and I want to thank AICTE Training and Learning Academy for this opportunity. I want to thank VAT, and more specifically, I wanted to thank Dr. Binu Ben-Jos and Dr. Premalata. So with that, I have only one question. Did you guys notice any anomaly in my slides? It is on every slide. It is on the top. It's even on the top of this slide also. And it's very, very barely visible. Can anyone answer? Okay. I just put the number 2 on top of every slide. Oh, that's a religious thing. It's not an anomaly, at least for me. So yeah, with that, I want to say a big thank you to everyone, and I want to transfer this back to Dr. Premalata.
So, sir, thank you very much. So, Premalata ma'am, can I continue?
Yes, sir, please, sir.
Dear participants, today we have Mr. Jayakumar Kannan, Director, VLead Consulting Canada, and he has given a lecture or presentation on anomaly detection in electric vehicles. Dear sir, the topic you have presented in this session is really very interesting and is new for most of us. And we can really visualize a good research potential in it.
Okay.
And also some opportunities to do research. The coincidence of this presentation, I mean, the real-time system with the latest research trends is really amazing. Okay. So on behalf of VIT and the participants, we thank you very much for such a wonderful session, sir.
Sure. My pleasure. Thank you.
Thank you very much, Jayakumar, sir. Thanks
Not
for
a
joining
problem.
us. Okay,
Not a
sir.
problem. Thank you. Good luck.
Thank you. Bye, sir.
Now we can wind up the session and we can resume the session at
Ma'am,
11:30.
we can give the details for the next session. I think we are on time, and therefore we